So my session is inventory characterization. I lead the SimCenter AI team at UC Berkeley, and it's my great pleasure and honor to be here to share some of my experience on that project. Machine learning, in short, is about predicting Y from X. That's our 6-step recipe when I teach machine learning at UC Berkeley. The most difficult part, as Devika pointed out, is about turning the data you have into a representation, vector space X and Y. What is your X, what is Y? There's selection involved, there's domain expertise involved. This is where the domain experts and machine learning experts should interact. And just like any scientific experiment, you need to first, a priori, when you start the scientific journey, you need to figure out how do you benchmark your success? What is the loss that measures how well a model f of x can predict y? Step 3 is to pick a family of functions that might predict y from x, because all we have are usually discrete, isolated observations. They are not linked together. In order for you to predict some unknown new instances, you have to link them. And they're usually parameterized by certain variables to represent the family functions. And that itself encodes what you think the noise might be. How much noise is in the data? Just like when we fit a line, if we choose a straight lines, that's, you know, yeah, it's a coarse grain. If you allow more curvious curves, then you think every wiggle is signal, not noise. Okay, so then the step 4 is collecting the instances. And usually nowadays when people do data science or machine learning system, usually the data are given to you. And by purposely putting this at step 4, we want to advocate this really should be done in this experimental design way. You have to set out a goal, design, you know, the benchmarks, assess, pick your family, and then try to choose what to collect from the field. And then you do the optimization. That's, you know, once this is done, even the model is optimal according to your loss, that's not necessarily the best for your application. So you have to validate on new data. After all, it's all about prediction. And this is a one slide review about what deep learning is about. You have image, you want to predict what the semantic class of this image is. Through a succession of composition of simple complementary elementary functions, you build a hierarchical representation in completely data-driven learning fashion. So it goes from pixels to parts to objects to scenes. Finally, the semantic. This is a bike, right? And the machinery tells you how to optimize this, how to figure out the best parameters through this end-to-end learning with a technique called error backpropagation. For the SimCenter project, the role of AI team is highlighted in this box in yellow, right? You can have all the analysis you can do before the, prior to earthquake, for example, after the earthquake, but where do you get all these building models, realistic, large scale, regional scale? And this is where we come in. This is a building information model, specify completely the geometry. So we call the BIM. Currently, the state of art for the structure analysis model, so-called SAM, for simulation is done manually by engineers. And for those people in the field, they will tell you no two structure engineers will give you the identical model, given the same BIM model. And which one is best? It's hard to tell ahead of time, right? So what our goal is to turn this into a virtual structure engineer. And this behaves like it has split personalities. You know, it can behave like multiple real, actual structure engineers. This is our job. We learn from small set of engineer data examples and try to capture the knowledge in it, and allows us to do the BIM to SAM, automatic translation. So again, so what is our first step? How do we choose that? This is the most difficult part. And you know, I show you the BIM, an example of BIM. It's not even a complete model. It's just a component of that BIM to the SAM. In reality, these are represented by JSON files with structural language. We are not going for JSON to JSON directly, right? Those letters and the characters don't mean a thing. We have to extract features from that. So what we do is, from the JSON file, we extract some BIM features. We talk a lot with our collaborators on the team, and we also extract features from the SAM file. And then we train, with the paired data, we can learn neural net to model the association. Once we have such a model with the SAM feature, we produce the SAM file, and it allows structure engineers to do simulation. With the simulation, we match those sensor data in the field, and we can quantify how good the SAM model is. It provides a model score. And with this new additional information, we can come back and build another neural net model. You know, if I want to ask for a good quality SAM, can you give me one? Okay, so this is with the simulation in the loop. It allows us to quantify how good the SAM model is. The task, so that was BIM to SAM, automatic translation. Our task 2 is, where do we get the BIM model to begin with? Okay, and for the last year or so, we've been focusing on so-called image to BIM, IM to BIM. Since I'm a computer vision researcher in training, so the overall flow is like this. Let's say we have some images. It could be Streetview photos. You can collect from multiple views. And you may have some metadata, you know the GPS location, you know the camera pose, you know the camera calibration. And you could have, you hook up with the public records when the building was built and other related information. All of these could be fed into a model. And instead of going for the straight, structural element features, we go for properties. These are latent variables or hidden variables, but for the sake of modeling SAM at the end, but the properties such as soft story, which is important for earthquake engineering, or the type of roof before wind, hurricane analysis, how much pitch there is in the roofs, or the height of the building, the physical height. You can infer the height from the images or the number of stories. These are different aspects of properties of interest to structural engineering. And with that, all these, you might realize a large scale regional model through these properties indexed into some stock models. That enables you to do more accurate large scale simulation. That's the pipeline. So our job is this part. From images, from metadata, how can you model properties of interest? And this list is through the discussion with the structural engineering, natural hazards engineering people in the field. In the past, I had a Samsung project, and they want to figure out the material property of buildings for the sake of planning radio frequency signals. A lot of Samsung handsets, if you move around in urban environment, the signal gets bad depending on which location you're at. But how they want to do it realistically. But where do they get all these building information? And when we don't get a good signal, we usually go to the windows, right? So, so how do you know that? So from these Streetview photos, they pick out a set of material properties of interest to them. Wood, concrete, curb, tree, so on and so forth, and windows, glass, right? So these are our results, segmentation results. But even with this, it's too much work in a way, because they want to map out the whole United States, right? It's a large scale effort. So can we do it faster? Let's go for aerial images. Given the aerial images, can I map out, just ballpark, is this a concrete building? Is this wood houses? Because we can figure out the glasses, I can actually give you all the windows. You can buy 3D models from some companies purposely scanning this, but you never see anything like that on the market. I can give you buildings with windows, and they our Samsung collaborators call them microstructures. And this is actually now deployed in the field. So where could we get such data? You know, there are a few links about San Francisco. You can get building footprints. They have height, they have GPS locations. These are all public records. There are building permits, more than 1 million records. There are a number of stories, construction types, coordinates. And then there's a land use, which years the building is built, the GPS coordinates. With the GPS coordinates, we can align all these different records. And of course, there are, you know, where do we get these visual data? Google Earth and Streetview, one of our collaborators. Unfortunately, they cannot come. They also have, you know, the issues I'm going to get to. And Microsoft Building Footprints, which Nobosha is going to talk about. And OpenStreetMap, it's a community effort, open source effort. All these are the sources we have been looking into. The challenges are, all these different data sets have different formats. How do you align them? You know, and then with the private sectors, they always have the issue of, you know, do you buy from us? Is available for public research? And then probably also security concerns down the road. So all of these issues, these are very practical issues. Here's an example of what we get. We do the Streetview photos. We use the script to crawl for these photos. And these are some examples showing the number of stories of each of the building in the photo and the construction type, so on and so forth. I'm going to tell you another thing we have done on soft story classification workflow. Most computer vision benchmarks out there, they are concerned with the semantic classes, like does this image contain a cat, dog, right? But for structure engineering, these are some specific, highly specific structure information. And this is not anybody can annotate, you need expertise. And this project illustrates additional sets of problems. For example, this is our workflow. We started with collecting our data, visual data, and this metadata. We only have, so we collected over 5 cities, Santa Monica, Oakland is in the Bay Area, Berkeley, San Jose, and San Francisco. San Francisco data not used currently. We have our structure engineers to annotate a small set of buildings, like 1,000 over the Santa Monica data. These are available, and about 395 on the Berkeley, San Jose area. We use Santa Monica and Oakland data for training, but we don't have annotations for Oakland, and it was there for a purpose, because you can't annotate everywhere. Right? That's a real challenge we want to deal with. So we have some manual annotation. We use that to train a small classifier. It's like we want to bootstrap from small. Of course, whenever humans are involved, there's noisy expert annotations. We build a first stage classifier, and we use this. We apply it to the rest of Santa Monica data and Oakland data. It will spread out some predictions, and we use them as if they are ground truth, okay? And then we reserve the Berkeley annotated data as for testing purposes only. They never see anything from Berkeley or San Jose, okay? And when you come to the design of the deep nets, you have a lot of choices. What architecture you use, overall the framework is a classification into 2 classes. And you get some results, and our currently, for example, with the ResNet 50, we get these test F scores. And once you get the results, you have to go back and see whether the classifier is basing on the right part of the image to make this decision, whether it makes sense. So the challenge we encounter, aside from bootstrap from small noisy data, is that there's a huge class imbalance. There are a lot of non-soft story buildings out there. Soft story only have, small fraction, right? For classification, if majority is, 99% is one class, 1% is the other class, you don't need to do anything. You always say that, this 99% class, and that gives you 99% accuracy, and that's useless, right? So how do you deal with that? And then there's this cross-region generalization in computer vision, machine learning is called, cross-domain generalization. But houses in Santa Monica look very different from houses in Berkeley, for example. So you learn on that data how much confidence you can give to the test performance to a new city. And then the visual data is not perfect. It's just some proxy we could ever get. There's occlusion, the houses may be occluded by trees, so on and so forth. All these challenges people have dealt with in vision and machine learning. I'm going to focus on one thing in the rest of the time from my group. The problem I want to deal with is this small annotations or even no annotations. Let's say some people, you are dumped with all these images, but no one tells you what they are. That's a problem a baby faces, right? You can't tell baby, this is a cat, this is a dog. He wouldn't have no sense what it is. But just by the mere exposure to all the visual input, can the baby learn something? Recognize the visual input? And how would she indicate to you that she has learned something? She learns how to see. I think there are two ways. One is from data analysis point of view. If I dump you a lot of data, at least you should be able to answer me. How many basic patterns are there in the big data? Data is is plenty out there. But I want you to give me an abstract, a summary. How many basic patterns are there? Secondly, if I give you a new image, can you retrieve images of similar characteristics? So what is an image? Image is nothing more than 3 intensity arrays in red, green, blue channels. And each number, the larger the number, the higher the intensity of light in these channels. If I remove the images, and these are the problem really face computer vision scientists. These are just numbers. The naive approach is, you concatenate all these numbers into one long feature vector. That's your signature for each image. Then you do the color retrieval, essentially. Every image has this feature vector, and you have a set of images in the data set. You try to find the images with the shortest distance in that feature space. So the first one is a query. The rest are nearest neighbor in this big ImageNet data set. And this one does not require any labels. And you look at this is not too bad. Essentially, it's picking out, it's acknowledging there's bright objects against a dark background. But it doesn't care about the semantics. It could pick out lipstick, puppy, chef, or cell phone. It said, can we do better than that? I'm not interested just picking a bright object. This is a result trained with this 1.2 million ImageNet labels with 1,000 predefined labels, cats, dogs, so on and so forth. Now everything the method picks out is highly semantic correlated. It only picks out seems like the same model in different poses in the same dress. That's great, right? The second row is our result. You trained on the ImageNet data without using any labels. Our results are getting close to the labeled training problem, right? You have learned visual similarity. If you think about it, it's remarkable because visual similarity is a tricky business. One day you want to say, search by color. Another day you might want to say search by texture, right? It's very tricky. This is a data-driven visual similarity. You give me the data, and that the collection, the ensemble of the data impose certain similarity. And that's what we are discovering through learning. And if we have this data-driven similarity without requiring any labels, but if the data, the labels are ever available to us, we would like to use it. And the last row is our results that incorporating the labels. And I will claim that our results are better because the label for the query image is dress. Now we are focusing on the part of the visual characteristics that defines what a dress is. It doesn't matter who wears it, how many models are wearing it, okay? And this is our result using just ImageNet pre-trained feature learning model, unsupervised. This is second row results, okay? We haven't seen any soft story building, no instance. Just apply this out of box to our Streetview photos. And again, the first column has the queries and the rest of the columns are nearest neighbor retrievals from a label set. And because we have the label, we know which one is soft story, which one is not, okay? These all happen to be soft story queries, and the green box indicating the nearest neighbors are soft story instead. And through this, we can actually get a sense, for this, for example, this one, all the 5 nearest neighbors are soft story. I can assign a class to the query. I know that in that part of feature space, it has a high density of a soft story. So I can have this confidence measure attached to the classification. The bottom ones are the low uncertainty. I don't just have a class label. I also have the quality of my classification. So, and these are preliminary results. We have more detailed analysis going on. And I'll end my talk here and introduce my colleague in computer vision. Nabosha is a senior research principal at Microsoft Research AI group. And he leads the AI efforts on Earth, the land cover mapping. I'll give, without further ado, I give my, that's right, Zoom. I'm gonna stop sharing.
As they're changing, I think we should